All right, I think I can get started. Good evening, everyone. My name is Ibrahim, and I'm your VGS chair for the 2025-2026 season. Some announcements before we get started with tonight's talk. So if you haven't heard already, the symposium date has been set to June 5th at the Paradox Hotel downtown. The call for abstracts has been sent out, so be sure to poke your people and let them know to send those in. The deadline is early February. Our next talk will be a joint talk with the Tunneling Association of Canada. We've done it annually. It's usually been at Steamworks. It'll still be at Steamworks on January 28th, and where we'll have Herenecht speaking. Dr. Hutchinson will be speaking on February 9th at UBC. That will be our joint VGS GeoRocks talk. And then February 25th will be our joint talk with EERI. That'll be at the Royal Vancouver Yacht Club out by Jericho Beach. So stay tuned for that announcement. And then May 21st and 22nd will be our spring short course. We'll be flying in Dr. Yusuf Hashash, where he'll be talking about seismic site response, soil structure interaction, and liquefaction using deep soil. You'll get the notification for that short course sometime this month, probably closer to the end of the month. So now I'd like to introduce our speaker, Professor Ribu Dhakal. Thank you.
Okay, well, thank you very much, Ibrahim, for the introduction. And firstly, thanks to VGS for the kind invite to deliver this technical talk. For those that don't know, hello, my name is Ribu. I'm a newly joined assistant professor at UBC, but I'd spent many of my former years doing research out in New Zealand. And so what I'll present today is a culmination of some of the work that I started back there, but is ongoing as well into some of my work here at UBC, focusing on new approaches for simplified evaluation of building settlement due to seismic soil liquefaction. Normally in this presentation, I don't add the word seismic, but I know the context here, liquefaction can mean static. And so I add that word here just to reiterate it is from an earthquake source. So this is kind of the outline of today's talk. So we'll give a quick background on building settlements due to soil liquefaction. And as traditionally done in geotechnical engineering, we'll start with looking at case history observations. And we'll use that to guide our understanding of what the key features are that tend to govern the response. And then looking at perhaps some analysis, design, and considerations. Then we'll focus on some current state of practice for engineering assessment of building settlement. And my objective after the first 2 points is that in about half an hour's time, everyone in this room will have a rough understanding of what the key issues are that we want to tackle in preliminary design. Okay, so when we're using a method, we want to know what key features that we want to capture. And then I'll propose some of the new approaches that has been published in some recent papers as well, and try to tackle some of those issues that I preface in the first 2 points before I conclude the talk. So let's start with a background. So we'll look at case history observations, and liquefaction is a phenomena that I'm sure many of you know causes soils to lose its strength and stiffness, and so that can result in a wide range of effects of buildings. In the most extreme case, and probably the ones that make the headlines, are the bearing capacity failures, where we have the famous Kawagishi-so apartment buildings from the Niigata earthquake on the left, and then some more examples that we've seen in Turkey, for example, in the Kocaeli earthquake. For lightweight buildings, residential buildings as well, often this manifests in the form of tilts and settlements, and so Christchurch had several examples of buildings that had a few degrees of tilt and several tens of centimeters of settlement. In some cases, if we have buildings on piled foundations, you might often get these types of cases where you have movements of the ground relative to the building. And so this is an example from the Kaikoura earthquake. Not really a case we'll look at today, but I thought I'd put it in here as for completeness. And then more recently, actually, from the 2023 earthquakes in Turkey, there's been some interesting studies looking at interaction effects between buildings. Here is an example of what looks like a hookah bar that sits between two larger and heavier buildings, and you can see the settlement of those two buildings is causing this kind of hogging ground motion, and that's kind of controlling the response there as well. And so this is some interesting work that's also coming out of some of the recent earthquakes. In terms of just focusing on bearing capacity, well, we know why that's happening. We know that liquefaction causes a decrease in stiffness and strength. And so if we imagine and visualize what's happening in the soils during liquefaction, well, it's kind of illustrated with this diagram where you can see the individual grain particles are actually not in contact with each other. And so there's not really much load transfer mechanisms, which can lead to a loss of stability. And for heavy structures, this comes in the form of tilting and overturning, and that's some of the pictures that we saw in the last slide. And then for lightweight structures, you might see it manifest in the form of excessive global and differential settlements. And just note here that these configurations that you see in these images, it can take tens of minutes to reach there. It's not going to happen straight away during the earthquake, but often manifests in this form a few minutes or sometimes even tens of minutes after the earthquake. We also find that actually in cases where there's ejecta manifestation, these effects tend to be exacerbated. So ejecta manifestation being the case where we have liquefied soil that it's made its way up through to the ground surface due to some cracks and fissures that are formed. So it's a hydraulic process of liquefied soil. And often we find that these are concentrated around the edges of buildings and footings. So you can see some examples here of ejecta that have really been concentrated around these edges. And these are evidence of settlements due to soil loss as well. You could imagine that once the soil has left a void in the ground, that void must be filled by the soil around it, and so that leads to additional mechanisms of settlement. And this is exacerbated for shallow liquefaction cases. And so this is an interesting consideration that you might want to include in addition to our traditional volumetric and shear-induced SSI effects as well. Just to really drive home the point of shallow liquefaction, here's a case study of a building. This is the CTUC building from Christchurch. So this was a building that's quite well studied actually, that liquefied. And below the building is a schematic of a cross-section, and you can see two CPTs there. On the left-hand side of the building is one CPT, on the right is the other. And you can see it's showing you profiles of the soil behavior type index, I sub C, plotting to the left of this line, and the corrected cone tip resistance, the QT, plotted to the right of that line. And the shaded regions are indicating soils that, according to existing simplified procedures, had liquefied during the earthquake. And you can see on the right-hand side, that zone is really quite deep, right? We're seeing liquefaction occurring at about 10 meters or greater depth. But on the left-hand side, though the cumulative thickness of liquefied soil is equivalent, right? If we sum up those thicknesses, it's probably similar, but it's much shallower. It's at about 2.5 meters depth. Shallow liquefaction, of course, tends to increase potential for ejecta, and in this case, we saw sand ejecta near the left-hand side of this cross-section here. And so this resulted in these differential movements that you're seeing out here, right? So you saw in the order of 25 to 26 centimeters of settlement on the left-hand side of that image versus much less on the right-hand side. And so the key takeaways here is that shallow liquefaction means increased potential for shear-induced settlement, for ejecta-related settlement, and differential settlement. And to drive home the point of differential settlement, uniformity or let's say non-uniformity in the soil or structure also tends to increase these differential settlement potentials as well. This is a nice video to illustrate what I'm referring to with some of these features. This is an exaggerated demonstration from some of my colleagues back at the University of Canterbury, but it's a nice shake table experiment that we do. So you have a shake table at the bottom, and this is a box of sand loosely deposited, and the groundwater table is pretty much at the ground surface. It's slightly below the surface that you see, and we'll focus on the heavy structure on the right and the lightweight structure on the left. And so once we start shaking, we'll slowly increase those pore pressures. We're not seeing those effects straight away, but at some point you're going to get shallow liquefaction, and then a few seconds after that we're going to see the effects coming in the form of excessive tilting. You can see it's very, very exaggerated, and in lightweight structures it's settlements. Of course, we're also seeing ejecta manifestation here, and that's also another feature that tends to come out. Hopefully our buildings are not doing this level of damage, but it does give you an exaggerated demonstration of what's actually going on. Okay, so that was a quick overview of some interesting case histories, but the idea now is to start collating those and understanding what are the key effects that plays the most governing role in some of the responses we're seeing. And this is a nice summary of perhaps some of the features that plays the most important role. This is not everything, it's not encompassing everything, but it tends to be ones that governs the most. And in terms of soil properties, we find that the thickness of liquefied soil layers, the depth of the liquefied soil layers, and the properties of the liquefied soil layers tends to play the most important role. There are other features, but this tends to be a key feature itself. We've already talked about sorry, give me a second. We've already talked about the importance of the depth and thickness, but you could imagine the properties as well play a role. If you have a loose soil that's, let's say, contractive, then it might behave much differently to a dense soil. In terms of building properties, we're finding that the width and the bearing pressure tends to play a governing role. And then, of course, looking at rigidity of foundation, ground motion characteristics, uniformity in the soil properties, they all tend to play a governing role. And so our objective, and when we have preliminary design, we're looking at preliminary design objectives, is getting a good feel for what these are doing for our particular site of interest. Okay, so which of these are playing the most governing role for our settlement calculations when we're looking at forward design? In Vancouver, there's a nice task force. This was put together back in 2007. I'm a big proponent of this task force. I think it's got some excellent work in there. And it was a nice design guideline. I believe my understanding is that it was put together at the time to kind of ensure that the practice in British Columbia was up to speed and doing kind of the same or similar things across the board. And so it put together and compiled some of the recommendations of the profession at the time. And they have a nice component and section here on post-liquefaction settlement. Okay? And they say here for light structures, 1 to 3 story buildings founded on non-liquefiable cohesive crust over liquefied soil. So we want to think of it in terms of this 2-layer model. I'm going to put this up here because we're going to come back to this 2-layer model, and we're going to refer to this quite a lot during the later half of the talk. Okay? So we're thinking in the form of a foundation on some non-liquefied crust over liquefied soil. And we want to use this chart that was developed, I believe it was from some of Ernie's work as well back then. And it was used for the purpose of preliminary design. Okay, on the y-axis is the post-liquefaction shear-induced settlement, and on the x-axis is the bearing capacity factor of safety. Naturally, as the factor of safety gets lower, we expect the settlements to be larger. Okay. So now, having prefaced you with 10 minutes or so of already the key features that govern liquefaction, some key questions would be, can we capture those effects from the previous slide in this factor of safety calculation? Are we able to capture the effects of the depth, the thickness, the properties of the liquefied soil? Are we capturing the effects of the foundation properties, etc.? And if we are, how easily can we assess their sensitivity? Remember, we're doing preliminary design. This is not in the stage of detailed design. And so we want to understand those features pretty quickly. We keep reading on in the task force report, and the very next section says that there are no recognized analytical methods to evaluate bearing capacity at the time. And so we have this nice chart here, but the issue does arise in terms of having a robust method to calculate factor of safety. And so this leads to a natural challenge in terms of, well, how would we calculate settlement in this case? And so this brings us to the second point. Okay, so we've talked about background on some case histories, looked at some key analysis and design considerations. Let's have a look at what the current state of practice is in terms of evaluating settlement. This is my one slide overview on the simplified procedure, but it does help paint the picture. The key steps after site characterization. Following site characterization, you might look at some susceptibility. So for this schematic soil profile with 5 layers and a groundwater table, we might use, for example, CPT data to suggest layers 2 and 4 are liquefiable based on the soil behavior type index, just as a proxy. We would probably then follow that with a triggering procedure, and often we do a stress-based approach with factor of safety. Our capacity is often our QC1 NCS, our corrected clean sand equivalent cone tip resistance. And then our demand and our factor of safety is often a measure by PGA and magnitude. Those tend to be the earthquake inputs that we use. Then we look at ground settlements, and ground settlements often tend to be the superposition of different layers. So in our example here, layers 2 and 4, for example, could be contributing to the total settlement at the ground. And it's important to note that these interaction effects are ignored. So these calculations are performed independently for each layer, and they are superimposed to kind of give you a total settlement. And then we kind of look at effects on structures following that assessment, okay? And so we might want to then say, hey, let's take it a step further and look at global settlements and differential settlements. And this tends to be the flow of calculations. And there's a lot of details in each of these steps, and we can start breaking down some of those details. But I want to give the key takeaway, and this is kind of the essence of the simplified procedure, is it really comes down to 3 key features. You can group them into 3 categories. One is the site characteristics, right? You're looking at the profile characteristics, the material behavior within the profile. And so that boils down to these layers. We're using these CPT values as a proxy for expected behavior during cyclic loading. The ground motion characteristics, or the earthquake load, which we often tend to capture with PGA and magnitude, which tends to not do a pretty bad job for triggering, although there are other better measures out there. And then structural properties in terms of the building properties, the footing as well. Okay, so the width of the footing, the bearing pressure, etc. So these are the 3 key features that we're essentially trying to capture in these simplified procedures. So rather than going into the weeds, that's kind of the overarching three steps. Now for building settlements, what does that mean in terms of our calculation flow? So often we would maybe start with the schematic here. This is the case before the earthquake. You might have some sort of footing into the ground, and below that is some liquefiable soil. We would start with ground settlement, and this is essentially starting with saying, what is the settlement that we expect the site to occur at the site, independent of the structure being there. Okay, so we're essentially doing a free field level ground settlement, and that has often 2 components, a volumetric component and an ejecta-related component. Right? The volumetric we might be familiar with, that's the dissipation of excess pore pressures. The ejecta component being due to soil loss from ejecta. Apologies if that figure is a bit small, but it's due to soil loss from ejecta. And then we add, so it's an additive component, an additional feature or additional component to give us the building settlement. And this is the shear-induced component. Okay? And this is the current flow of calculations that we often do in practice. Okay, we start with the ground settlement, then we have an additive component for the building settlement. Well, let's look at the ground settlement. So we'll start with the simplified procedure, and we say, okay, SV. So our ground settlement, we might start with our CPT profile. So again, there's that parameter that we looked at before, right? The clean sand equivalent cone tip resistance. As a function of depth, we would go through all of our calculations, simplified analysis, and then use these pretty well-established charts to look at strains or volumetric reconsolidation strains. And so Zhang et al. Is the method that I'll be referring to. It's largely based on the work of the late Professor Ishihara. And their method essentially has 2 key inputs. One is the QC1 so that gives us the x-axis of this plot. The second is the factor of safety, which gives us which line to use. And then we read off that chart to give us our strain. So as an example, let's say at 5.5 meters depth, we would get a QC1 NCS of 120, a factor of safety of maybe 0.85. So you read off this chart and you get a strain of 1.4%. That's the expected volumetric strain at that depth. And then we integrate with depth to give us our settlement. Okay, so it's the exact same schematic flow that I showed earlier. The reason I'm showing the details here is it's important to highlight that I'm performing the calculations at each depth and I'm integrating them without any consideration of the depth of liquefaction, right? So these factors of safety, whether they're at low at the shallow end or at the deeper end, we would still get the same volumetric settlement because it's not accounting for the depth of liquefaction. Well, what about ejecta-related settlement? That would be the next component, and often we ignore it. Right? There's no well-established method out there at the moment, and so really we're using ground volumetric settlement as a proxy for the ground settlement. But it's important to remember that it's not accounting for the depth of liquefaction, which we know is a key feature for building settlement. Okay? So that's the ground settlement. What about the building settlement? So let's go back here and start diving into the building settlement. Again, this is the shear-induced component, so we have the volumetric. I put a question mark next to the ejecta because there are no methods out there at the moment, or well-established ones. And now we look at the shear-induced component. And we'll be focusing on the Bray and Macedo method. This is from a paper that was published by them as part of the Ishihara lecture series back in 2017. And their method essentially follows like this. Again, start from the simplified procedure. They start with the same framework. But then they have these two properties that are essentially a combination of soil properties and earthquake properties. Okay? Remember those three parameters that play a big role: soil properties, ground motion characteristics, and foundation properties. So they have these two parameters, HL being the cumulative thickness of liquefied soil. So essentially you're summing up all the thickness of soil where factor of safety is less than 1. And then they have this LBS parameter. It's essentially an integration of strain with a depth weighting function. Okay, so this is directly one where they're explicitly considering the depth of liquefaction. You can see the gradient of this line is much steeper at the shallow depth versus the deeper values, reflecting the fact it's a greater weight. So they have these sets of inputs. They have the foundation properties as bearing pressure and width, and then they have additional earthquake load demand parameters, and in their case they use the cumulative absolute velocity and the spectral acceleration. And now that already rings alarm bells for many people, because now you're inputting some time history parameters as part of your simplified procedures. So you already need PGA and magnitude to perform your simplified triggering analyses, but now you need 2 additional earthquake demand parameters, so 4 in total, to perform the full calculation flow. And from a simplified analysis perspective, that can pose some challenges. If you can get through all of that, you finally get your shear-induced settlement. Okay, so we have our volumetric, our shear, ejecta, question mark. Okay, so those are the 3 components. In addition to all of that, the entire calculation flow, we're often performing them at one given limit state, at a given seismic demand. So this is kind of a figure to illustrate this. So let's say you have a site. The first thing you might do is you might go to NBC 2020, check the hazard for the site, go, yep, this is the return periods that I'm interested in, a serviceability limit state, so maybe a 475 year return period, and then maybe a design ground motion at a 2475 year return period, and that might be associated with a given shaking intensity. And so you might extract, let's say, a PGA or a PGA and magnitude pair from your seismic hazard. Then on the y-axis of this plot, I'm going to plot some response measure. For the case of today's talk, it's building settlement. And so we might plot settlement on the y-axis. And often I see in practice, often only the volumetric component, which remember does not incorporate the depth of liquefaction, which we know is important. But in any case, if we compare 2 sites, one shown in blue and one shown in red, you would see they're pretty similar. Yeah, okay, looks like the blue side is maybe slightly higher than the red, so you might suggest, the red is a little bit better, but it's not too different. When in reality, we should be considering the response curve over the entire spectrum. Right? We're missing the key picture here, and so if you had the response curve as a whole, it's quite obvious which side is performing better. Site A is significantly better than site B. So you imagine the power of performing calculations across the entire load intensity and then bringing in the hazard afterwards. And so it's important to understand and evaluate the behavior of the system across the full range of relevant earthquake load intensities. In addition to that, we want to account for uncertainties. So each of those lines should have at least some error bands that realistically reflect the uncertainties in the response. And so you might have some plus or minus 1 standard deviation lines shown in dashed here. Okay, so that was a quite dense overview, but it does give us some context before we start looking at the procedure that I will propose from now. So to recap, current practice. We have volumetric settlement, our SV component. It's a CPT-based method that we're going to be focusing on, and it incorporates results from the simplified triggering analyses. And our seismic demand is a combination of PGA and magnitude. From now on, I'm going to use PGA 7.5 to reflect those 2 parameters. So we're going to combine those 2 to give a PGA for an equivalent magnitude 7.5 earthquake. So it's a correction that you can do. But essentially, whenever you see PGA 7.5, think a combined effect of PGA and magnitude. Remember, it often is used as a proxy for ground settlement, and sometimes even building settlement, which is a problem because we know it doesn't consider depth of liquefaction. Ejecta-related settlements, well, there's no established method, and so it's often ignored. And shear-induced settlements, which, current state of practice, we use a CPT-based procedure following a triggering assessment, but requires some time history parameters. Okay, so we need to extract about 4 different seismic demand parameters for a given limit state. In addition to that, it's difficult to ascertain the effects of key input parameters on settlements. So if you recall the calculation flow that I talked about, if I were then to ask you, hey, actually I have some uncertainty in my ground profile, actually my liquefiable soil is now slightly deeper, what's the effect on calculations? Well, you have to go through that flow again. If you're doubling your work. So each of those sensitivity checks that you might want to do, it's not very obvious from the very outright start what the effects are. And then lastly, I touched on the fact that we're often doing a discrete assessment at given limit states, right? For example, a serviceability and then an ultimate limit state, rather than considering the response over the full spectrum. So what I'll cover from now is what we refer to as the Dhakal method. It's summarized in 3 recent publications, and they are given at the end of this talk. I believe it's recorded, so you're welcome to go and check those papers, and I encourage you to do so. And I reiterate that this is a method developed for preliminary design only. Okay? And the key features are that, 1, it accounts for all 3 settlement components within a single framework. So we're not chopping and changing between different methods. It accounts for the range of relevant earthquake load intensities. So our outputs are given as response measures versus PGA, rather than at given limit states. It accounts for uncertainties in the assessments. And it's a simple model focusing on key factors affecting the response. It's more important as engineers for us to get a feel for what's playing a governing role than to hone in on the right number to the right decimal place. And so that's kind of the objective behind this method here. The key ingredient behind the method is this computational model. Remember in that Vancouver task force report that I suggested, they were already introducing the ingredients of this, where they were talking about a foundation on some non-liquefied crust over some liquefied soil. Well, we're going to follow that concept here. And the idea is to construct this computational model and check the key relationships for this type of model. And so we take a CPT data and we convert it to the simplified 2-layer model. So our CPT data, this is just one example, showing you a profile of our corrected cone tip resistance and our I sub C. We have our groundwater at about 1 meter, and you can see below 1 meter depth, it looks like some of the soil has I sub C of about above 2.6. So you might say that the liquefiable soil might be started around 2 or 1.8 meters. And so that will give us our crust and essentially define this top layer of our computational model, which is this crust thickness. Okay? We're going to start with assuming just a footing width of 1 meter, so just slightly embedded into the soil. And so this parameter TC is essentially the crust below the embedment of the foundation. Okay? And we can define that based on the CPT data. Part of the method is also then to look at the QC1 NCS values of the entire soil, and we've developed equations to basically compute a single weighted average QC1 NCS value that represents the liquefiable layer. And that essentially gives us our input for our soil properties, which is what I refer to as the QC1 NCS bar, or the average value across that depth. Okay? But it's an algorithm that essentially accounts for the thickness and the depth combined, because we know that that's important. So that's inherently a part of the procedure. And so with that 2 inputs, our thickness of our crust and our QC1 NCS, we essentially define the site properties or the soil properties of our 2-layer model. Notice the entire model is only 10 meters thick. We're limiting at 10 meters because we found that numerical analyses also suggested and agreed with case histories that liquefaction below 10 meters didn't affect the shear-induced component or the building settlement component significantly, in the order of less than 5%, roughly. Okay, so we said, okay, we're okay with removing 5% of those of that additional settlement and just limiting our case to the top 10 meters. Right, so we have our 2 properties that define our soil properties. The second important feature, foundation properties. In this case, we're keeping it as the foundation width and the bearing pressure. And then our earthquake load, which is our PGA and magnitude. So remember those three key ingredients for the simplified procedure, we're still retaining those features. And in this case, we're going to use PGA 7.5, but remember it's a combined effect of PGA and magnitude. So with this key ingredient for our method, we're going to start developing relationships for the three components of settlements. So we'll start with the volumetric settlement. I'm replotting the computational model in a slightly different shrinked form to give me some space, but it's the exact same computational model that I looked at before. And the goal here is to extract the key trends and relationships within Zhang et al. We're going to take their method and extract the key relationships that are embedded within the procedure. How do we do that? We did that by running a wide range of sensitivity studies. Okay, so we said, let's vary our QC1 NCS value from 30 to 150, so from extremely loose to dense liquefiable soil. Let's vary our crust thickness from 0 to 5 meters, and then vary our PGA from 0 to 0.7 Gs. And we basically perform calculations at every combination of these sensitivities. Okay, so cross combinations as well. We go through the procedure. For each case, we're calculating a factor of safety, and then we're going through the full Zhang et al. Procedure to calculate strain. So this is the same chart that you saw earlier, and then getting volumetric settlement. And we want to see what relationships can we extract from that finding. And two plots came out from that analysis. The first one is shown on the top right. So on the x-axis is T sub L bar, the thickness of liquefiable soil, essentially the thickness of this point here, or 9 meters minus TC. Okay, 9 meters minus the cross thickness. So as we're increasing our thickness of liquefiable soil, the y-axis is increasing, and in this case it's SV max, the maximum possible settlement that can occur at that site. And you can see that value is going up as QC1 NCS decreases. That SV max is reflecting this limiting strain line that you can see in this chart here. Okay, so it's reflecting the fact that up to a point you're going to get settlement, but any further increase in seismic demand, you're not going to get any more. It's a maximum possible settlement. The second chart that came out is how the volumetric settlement goes from 0 to maximum as the seismic demand increases. Notice in the top chart, I'm not bringing in the seismic demand at all. Then in the bottom, the x-axis is PGA 7.5. So as I'm increasing the earthquake load intensity, how does my settlement go from 0 to the ratio of 1, which is SV over S max, so it's the maximum possible settlement. Okay, so I'm going to blow this up here. Okay, so here's your chart on the left showing thickness of liquefied soil as a function of SV max, and then that second chart there. So let's take an example. Let's say you have crust below the foundation, so it's a 3 meter crust below the footings. Let's imagine that there's a 3 meter crust here. And let's say our CPT data and those equations from the paper, we extract them and you calculate a single QC1 NCS average value, a depth-weighted value of 125. And our seismic demand is 0.75. So you would go into the first line, our thickness of liquefied soil is 6 meters. You read off the line for this blue line is for a QC1 NCS of 125, and you'd get 120. So before you even bring in the seismic demand, that's the maximum possible settlement for this site, given these properties. Then we say, actually, our PGA is 0.25. What does that mean in terms of our lines? And you can see here it's going, and you could read off the chart and say, actually, you're at 75% of the maximum. Okay, and so you could combine those two together and say, yeah, you'd get 90 millimeters of settlement. Okay, and the paper has some recommendations on some uncertainty bounds as well, and I've just included that here to illustrate that as well. Okay, so that's the volumetric component. We're just extracting the key relationships. But you can already see the power of having these relationships in front of you, because if I then ask you, oh, actually, I have some uncertainty, my liquefiable layer thickness is actually only 5 meters. Well, I can quickly see the effects of that on my settlement calculation. Or if I have some uncertainties in my QC1 NCS, I have some lab data that suggests there might be something different, okay, and I can see those effects playing a role in these two charts as well. So you're visually quickly seeing those effects without too much additional effort. Okay, let's look at the shear-induced component. We're going to do the exact same thing. So we're going to take our computational model, and again, we want to extract key trends and relationships within the existing Brand-Macedo method. So we have the same set of parameters. We're going to do the sensitivity study just like before. For this case, we're going to assume the worst case scenario. I know this is an unrealistic combination, but bear with me. But this is the worst case scenario from their paper, and so we're going to take that with a very, very heavy load of 250 kPa and a width of 6 meters. I know it's unrealistic, but bear with me. We're going to go through the calculations, calculate the soil properties, look at their shear-induced settlement method, and calculate the shear-induced building settlement. And again, see what relationships we can extract from that. Again, we have the first relationships that we extract. You'll notice it's in a very similar format. Thickness of liquefiable soil on the x-axis, maximum possible settlement on the y-axis. And you can see as your QC1 NCS decreases, so as you're getting looser soil, you're going to get larger possible settlements. Then your second chart, again on the x-axis is PGA75, and on the y-axis is how that ratio goes from 0 to its maximum. Okay, so I'm blowing it up again. It's the same curves. I'm just going to explode it slightly and go through that example again. So we have the exact same soil properties. So we have a 3-meter crust or a 6-meter liquefiable soil, QC1 NCS of 125 and a PGA 0.75. Again, you read off this chart, you might get something like 210 millimeters of maximum settlement. Scale that by 21% according to the second chart. Combine them, you get 45 millimeters of shear-induced settlement with some uncertainty bounds. Okay, so that's the chart. Now, naturally, the question is, well, what if my building properties are not these specific values? And so there are correction factors that we, again, extracted from the relationships of the Brand-Macedo method. So, for example, if we had instead 100 kPa load and a 15-meter wide footing, we use these two correction factors, the top one being a correction factor for the bearing pressure. So you can see it goes from 0 all the way to 1 at 250 kPa. And then the second chart being the correction factor for the width, going from 1 for 6-meter width all the way down to about 0.7. And so for our example of 100 kPa, you would get a correction factor of 0.72 and 0.87, for example. And so if you multiply that by that 45 from the previous slide, you might get actually 30 millimeters of settlement. Okay. Again, you can see the beauty of these charts because I can then say, hey, if I want to actually save on settlement, what if I make my foundation really, really wide? Well, you can see the effect of that with this chart here very, very quickly. Right? So you can start doing sensitivity studies just visually or back of the envelope calculations. That's the idea of the preliminary design approach. There are also correction factors embedded in the procedure for non-liquefiable soils embedded within the material. So naturally, so far we've considered all of this soil to be liquefiable, but that's not always going to be the case. You're going to have some nature of this type where you're going to have liquefiable soil, non-liquefiable soil, liquefiable soil, and embedded. And there are correction factors. Again, one-line equations that you just add as correction factors. So that's a lot of simplification, right? We're taking the existing Zhang procedure, the existing Brand-Macedo procedures, and we're simplifying it to this two-layer computational model. How well does it perform? How does it compare to the existing methods? And so this is a comparison of 1,386 analyses. So these are 126 sites. We decided to take a wide range of sites from around the world. About a third to a half of them are from Christchurch. The rest are global case histories. And they contain a range of ground motion types. Okay, we have loose soil over dense soil over loose soil. We have vertically continuous, interbedded, all types of deposit types. And you can see on the left a comparison of our method. This is the shear-induced component versus the Brand-Macedo. And you can see majority of those case history comparisons fall within plus or minus 25 mils. On the right is a comparison of the Zhang method for the volumetric component. And while it's slightly more scattered, we're still seeing about 93% of these analyses fall within 25 mils. If you're at a preliminary design stage, if you're willing to compromise on 25 mils of accuracy with those existing procedures for the benefit of having those quick sensitivity studies and checks, that's what this method is offering. Okay, so we're seeing those benefits at the cost of some misestimation compared to the traditional state of practice. Okay. Hopefully so far so good. I think we've tackled the two easy components, volumetric and shear. The reason they were easy is because we had existing methods to base them off, right? All we did was extract the key relationships, have some algorithms to develop a computational model, and define them very well. That's all we've done. But for the ejecta-related, we run into a problem. There are no existing methods to do that with. And so we said, okay, well, how do we tackle this? And the concept really came from a myriad of research following the Christchurch earthquakes. Following the decade or 2 decades after the Christchurch earthquake, there were several tens of thousands of properties inspected, over 25,000 CPTs performed throughout just the one city, about 20 strong motion station records for multiple earthquakes, not just one earthquake, but multiple earthquakes. And so this gave us an unprecedented opportunity for study, right? It was the most high quality or densely array set of liquefaction manifestation data that we had. And so we said, okay, well, let's start by the set of data that we have the most confidence in, and that's ejecta area, right? We can easily, or at least very quickly, based on satellite and ground photos, map the outline of ejecta following earthquakes. And so here's an example of a site where we look at a 10-meter radius, a 20-meter radius, and then a 50-meter radius area around that location, and start mapping how much of that area was covered by ejecta. And so you can see these yellow lines here indicating ejecta coverage, the pink lines indicating slightly thicker ejecta coverage, etc. And we corroborated that with ground photographs. Then to add to that set of data, there was also a decent amount of volumetric ejecta, volume of ejecta settlement estimates as well. So we had measurements of thicknesses of ejecta, shapes of ejecta manifestation in triangular, prism, circular, etc. And so that gave us a measure of the volume of ejecta. And so if we just assume that the volume of ejecta is uniformly distributed over that site, given whether that's a small or large area, we considered 3 different definitions, we can say that ejecta-related settlement is roughly the volume divided by the area. That gives us a proxy for the ejecta-related settlement. And this was largely based on a series of work done by Zorana Mejic, who I believe is now in the University of Delaware, but at the time was a PhD student of John Bray in Berkeley. And she spent her PhD basically collating this database. And it was a very, very high-quality database of these types of work. So they had about 200 or 250 cases where they had good data like this. When we studied their database, we found that actually one key characteristic stood out among the rest, and that was the soil deposit type. We found that actually, depending on the soil deposit characteristics, the response varied quite a lot. On the left, I'm showing you a vertically continuous deposit type, mostly comprised of liquefiable soil. So you can see here, this is a profile of QC1-NCS, but this red and green kind of soil profile here is a simplified profile indicating soils that are liquefiable and non-liquefiable. So the red is indicating liquefiable material. And we found that actually these types of materials, while it might not necessarily all liquefy, during an earthquake, they all develop some excess pore pressures. And so actually these entire deposits tend to connect hydraulically and contribute to ejecta manifestation. So you have increase in pore pressure throughout the depth of the profile, which contributes to the overall profile response, leading to large ejecta manifestation patterns. On the other hand, if we look at the right-hand side, these are interbedded deposit types, and we found these are deposit types that you can see here, the green indicating non-liquefiable soil interbedded with these red zones, which are liquefiable soils. And while we find that actually the QC1-NCS values are pretty similar or even lower, you can see a value of 80 in the critical layer here versus 91. And so while we're getting perhaps even looser material, the liquefaction is isolated in different layers, and so they're not connecting hydraulically, and so there's kind of morphological features that limit ejecta manifestation. To illustrate and drive this point home, this is a summary of the data plotted in 2 different formats. So I'm plotting here, before we look at the graph, 24 of the highest quality case histories from Christchurch. So we trimmed all of that data down to the very, very best data set that we could get. So we're looking at 24 benchmark case histories, supplemented by just over 100 global case histories. And these are largely taken from Boulanger and Idris's triggering procedure, supplemented with some more cases from the next generation liquefaction database. And on both plots, I'm plotting on the x-axis, again, PGA 7.5, and on the y-axis, the ejecta area coverage. The left-hand side is showing you a plot of vertically continuous deposits with critical layer QC1 NCS values less than 100, and on the right, same critical layer properties, but interbedded deposit types. So we're not changing the properties of the liquefied soil. They're both loose material. One is vertically continuous, one is interbedded. And on the y-axis, you can see the ejecta area coverage can go as large as 100% for these vertically continuous sites, whereas they're very limited in the interbedded sites, right? And in fact, we found that actually none of the case histories even exceeded 15 to 20% ejecta area coverage. And so that tends to be a key governing role that is an additional consideration in our ejecta-related settlement. And so what was the procedure that we ended up eventually developing? Well, we said, okay, these are the three key controlling factors: the soil deposit type, whether it's this VC, the vertically continuous, or IB, the interbedded deposit. For the vertically continuous cases, the density of the liquefiable soil or the critical layer plays a role. And then again, our input seismic demand. And so we'd go and develop this first chart. Essentially, we're going to take our PGA 7.5, which gives us the value of the x-axis, read off one of these curves to then get the ejecta area coverage. So that's the entire percentage of the area that's covered by ejecta. Remember, we considered three definitions: a 10, 20, and a 50 meter radius. And you can see this one blue line here is the interbedded deposit line. And so this is showing you that actually interbedded deposits, regardless of the properties of the liquefied soil, will really be limited in terms of ejecta area coverage, whereas the vertically continuous deposits can go from low, so you can see critical layer QC1 NCS values of 130 to 150 are down here, whereas if it's around 50 to 100 to 110, they can be as large as 100%. And so the properties of the critical layer is important. So the left-hand chart will give you the ejecta area coverage. And then from the data in a similar basis, we developed the right-hand curve as well, where we would go into this x-axis, input our ejecta area coverage that we got from the left plot, and give us our ejecta-related settlement. Okay, again, using the same principles as we've covered so far. So you'd imagine a vertically continuous deposit would give you a much larger settlement than an interbedded deposit. The left-hand plot is not very obvious, but I'm going to replot it in a different way. Okay, so we have PGA 7.5 and QC1 NCS. I'm going to plot them as PGA 7.5 versus QC1 NCS. And so here I'm plotting it in the traditional triggering format. It's the same relationships, but just plotted in a different way. Perhaps we're more familiar with this format of the plot. And so I'll show it like this as well. The red line is showing you the triggering relationships of Bullinger and Idris. I'm converting their CSR values back to PGA 7.5. Their data is open source. It's a simple one-line calculation, but you're converting their CSR to a PGA 7.5, and we're comparing our method to their triggering procedure. And you can see the beauty of this is that we're going to move beyond binary yes-no predictions. Now we're seeing that the further away from this triggering line you get, the more potential for ejecta manifestation. Right? So if you're at the top end of this chart here, we're really at the area where there's extreme potential for extreme ejecta manifestation, which is defined as 50 to 100% ejecta area coverage. Okay, and just to recap, remember the three key features: soil deposit type, density of liquefiable soil, seismic demand. Okay, so this is maybe a chart that we're more familiar with. Okay, so to round it off, let's recap and overview and look at the overview of the method. Remember, the key reason for, or the key ingredient behind the method is this computational model. We have our soil characteristics, our thickness of our crust, and properties of our liquefied soil. I discussed the fact that when converting a irregular CPT data to a single value, the equations naturally consider the effects of depth, thickness, and QC1 NCS of the liquefied soil. Our foundation properties, the second key ingredient, which we're capturing through the width and the bearing pressure, and then our seismic demand, which we're capturing through PGA 7.5. And the outputs of the model look as follows. So this is kind of the typical output you would get from performing these calculations. So on the top, I'm showing you volumetric, shear-induced, and ejecta-related settlement as a function of PGA. And the beauty of this is you can see which of the three components contribute the most as PGA changes. At the low PGA values, you can see that volumetric settlement, this is just for one example on one site, but it does illustrate that here we're finding the volumetric tends to govern the response, whereas in this end, maybe it's the volumetric and the shear-induced that tends to both govern the response. We can combine them to then get the total building settlement, and so you can see here the building settlement with uncertainty bounds as well, or just the ground settlement. And you can see the difference between the red and the black line is that additional shear-induced component. And you can see it starts playing a role in these larger PGA values for this site. Now compare that to the traditional standard of practice I covered at the start, where you would just perform a volumetric calculation at two values, so you would get this point here and this point here. And so you see the power of evaluating this type of holistic approach so then you can understand what the key governing features are of the response. Remember, SV does not discriminate between shallow and deep liquefaction, and so using that as a proxy for building liquefaction is a problem. While we know shallow liquefaction is increasing ejecta-related and shear-induced settlement in our method, it's important to include engineering interpretation as well. What is this method not capturing? Well, perhaps there's significant distress and ground surface irregularities. Perhaps there's potential for cracks and fissures and instability as well on the crust, and that can contribute to ejecta manifestation or no manifestation, and that's not inherently considered. So that's an additional interpretation from the engineer that's required. Maybe differential settlements are of concern, and how you want to convert that to differential settlements is also an additional interpretation as well. And so it's important to just also step back and think, what are some features that are not being captured, and including those in our considerations. This is just a quick flow chart just to round it off. So recall the three input parameters, site conditions, building, and earthquake load, define our computational model. From there, we can then calculate our three components of settlement, volumetric, shear, and ejecta. And then we can get ground and building settlements, so combining volumetric and ejecta to get ground settlements, adding shear-induced to get building settlements, and then considerations of uncertainties, plotting them as a function of PGA. Now, while the method is summarized in those papers, there is a spreadsheet tool that is available on DesignSafe. So it is free to download. You can go on there. You can see it's already been used quite a few times. But that has links to the three papers, so you can then go and read the papers if you want. Pay attention to the version number, given that this is research work that is still ongoing. There could be a future version. And you'll find that there's two spreadsheet links at the very bottom for you to download. Okay. The first spreadsheet is called the two-layer model, and it's a very simple concept. You're converting your CPT to the equivalent two-layer computational model. Okay, so this is just a snapshot, a peek inside the spreadsheet, but you would input some CPT values. There's some parameters that you can play with, and essentially gives you our computational model. I don't know if it's very obvious, but you can see here TC, the thickness of the crust is 0.3 meters. There's our QC1 NCS values, etc. There's our deposit type, vertically continuous. So that first spreadsheet gives you the two-layer computational model parameters. The second spreadsheet allows you to perform the settlement calculations. And so you can see here, one set of inputs is the earthquake load, that's PGA and magnitude. Then we have our foundation properties, our width and our bearing pressure, and then our soil profile characteristics as well. And you'll notice these are the same as from the first spreadsheet, so you can copy them over for that given CPT if you want. And you get quick outputs like this, so you get the volumetric, shear-induced, and ejecta-related settlements with uncertainties. You can see in terms of the bar chart which is contributing the most for your PGA, where that settlement estimate sits in relation to the overall response as a function of PGA. So these are outputs that you get straight away. If we dive in, there's other plots as well, so you can see where your site sits in those charts that I showed earlier. So this is the maximum volumetric settlement versus thickness of liquefied soil, one of the many charts that I showed, and you can see where your site sits relative to the overall plot. And again, quickly visually look at sensitivity of key parameters. And there's plenty of other sheets and charts as well. I won't go into the details, but this is just a peek inside what is available. Okay. Well, thanks for sticking with me on this. So just to conclude, liquefaction-induced settlement of shallow foundations, Three controlling factors in line with the simplified procedure. So we're looking at preliminary design, soil properties, so thickness, depth, density of liquefied layer, building and foundation properties, width, bearing pressure. A component we didn't consider is flexibility of foundation, irregularity of these properties, etc. And then ground motion intensity, amplitude, duration, frequency, content. To be consistent with the simplified framework, we're using PGA and magnitude, but it's important to recognize these other features may play a role as well. The Chubrinovsky-Dhakal method that I covered, well, that one places a great focus on integration of the three settlement components into a single framework, so you're no longer working between frameworks. Holistic consideration across the range of PGAs before you bring in SLS or ULS cases. So you're looking at the response before you even look at the NBC, for example. Allows for quick and easy evaluation of sensitivity of settlements to key parameters, and allows for engineering scrutiny interpretation, for example, inclusion of uncertainties as well. The key reasons: one is it's utilizing a simple two-layer model with rudimentary geometry, so we can, as engineers, quickly visualize and understand the effects of key parameters, extract relationships embedded into existing methods, and then developing a new conservative empirical procedure for ejecta-related settlement. Some ongoing work that will be part of some of my research here at UBC is actually supplementing this with looking at post-liquefaction bearing capacity. And a lot of centrifuge data has suggested there's a key difference in the response of cases like this where we have this punching mode of failure versus more general mode of failure, and so looking at those effects and then translating that to differential settlements as well, getting a good idea for what really is affecting differential settlement is some ongoing work as well that I'm looking at. Just want to acknowledge the two key co-authors, of course my former supervisor, Professor Miško Chubrinovsky, and also Nikos, who's now at University of Pavia. They were co-authors in this paper. Contributions as well from Dr. Mark Stringer, Professor Bray, and Dr. Capolato as well for some discussion and comments, and general wider collaboration over the past years as well. I do also want to give a shout out to my colleagues at UBC for helping me assimilate these last few months as well, and I'm sure we'll continue to support some of this research work that'll be ongoing as well. These are the key references, so 2 papers for the model development. The Ejecta model in particular, because that's a brand new method, there's a bit more focus on that one, so there's a 3rd paper from ASCE on that. And then the spreadsheet tool as well is given. So if you do go on the spreadsheet tool, you'll be able to get links to all the papers anyway. Otherwise, just flick me an email. I'm happy to pass the papers to you if you can't get access to them. Not a problem. Some other references that are there for if you are interested, but otherwise, thank you everyone for your time, and I'm happy to take questions.